So thanks for letting me explain a little bit this part of the work we are conducting with the friends and colleagues from ARIA. So first of all, the talk is in collaboration with the work is in collaboration with Tommaso, and in some sense it's a prolongation of what he explained. So of course the work came out of many different discussions with our colleagues, and in particular with Michel Bergman, Angelo Iollo, which I would like to acknowledge here, and of course Haitham Telibi. Okay. It will be, so let me make just a very brief introduction to the idea. So it will be technical in the sense that it is methodological to get nonlinear interpolations between two snapshots. Okay, so it is limited in a sense, but in this talk, but you can use this methodology to fit it into different kind of reduction strategy techniques, which can go from data augmentation to reducing the Kolmogorov n width. Okay, so I won't too much discuss that, which is probably this will be most probably the real applications. So I will focus here on the technique to get there. Okay, so as the title is saying, I am concerned with mappings. So so which kind of mappings? These mappings will be of Monge type, meaning that the way to find the mapping is basically by optimization, and the optimization is to find the map here, capital X, which minimizes the cost of going from Xi here to capital X there, provided that we weight this distance by the mass that we are transporting, and the mass is rho 0 times delta Xi. Okay, so this problem has an infinite set of solutions. If we look into the solution continuity, meaning that you have a rho 0, which is exactly, so a density, a probability density function rho 0, which is exactly mapped into a probability function rho 1, then this minimum has a unique solution, which is the gradient of a potential. Okay, so that's a very nice theoretical result. I won't discuss it. So let's assume that we have a technique to solve this Monge problem, which allows us to go from a probability density function rho 0 to a probability density function rho 1 in an optimal way. Okay, and this optimal way is basically this weighted distance here. Okay, once we get this optimal map, which we'll call it capital X star, then, and that's the interesting part, we can define a so-called geodesic map, which is basically a convex combination between the identity and the map that we just found. Okay, so thanks to this map, we are able to somehow interpolate rho 0 to rho 1. And this interpolation is very natural, as I will explain, I will show in one moment. So the way to find the map in general is not easy. It implies the solution either of an optimization problem or the solution of nonlinear equations, as I will discuss in a moment. In image treatment, they have an approach which is extremely efficient, which is basically it's based on the KL divergence here, which is a kind of regularization of this problem. But the fact is that you don't get the map, you get directly the interpolation, which can be good for data augmentation, but it's not necessarily what we look for in general. But I will discuss as far as I can in a second this issue. So basically what I was telling you is that I have a rho zero here, okay? It's a probability density function, which is represented by these two hills, okay? And then I would like to map this rho zero there to the rho one on the right, which is a hill which is higher, and the integral, of course, these are PDFs, so the integrals are one on the left and on the right. And what you find basically is this kind of mapping, and that's the interpolation which is induced by the mapping, the convex combination of the identity and the mapping that I told you. So it's an extremely natural way of interpolating these density functions. You see that the densities are joining without making a shock, which is quite remarkable, and it perfectly fits the density of one. Okay. Now the difficulty here is that when we can play with PDFs and everything is fine, the difficulty here is that in general we don't have PDFs, and we would like to interpolate between physical quantities which may not be positive and whose integral is maybe not constant. But we could get around this problem, and some time ago, exactly with Haitham Taleb and Michel Berman, we looked into a problem that was proposed by Airbus. It was an oscillating airfoil in transonic regime. So this pitching airfoil underwent the well-known hysteresis phenomenon, which means that in terms of the lift coefficient here, and as a function of the angle of pitching, well, you have an orbit which does not come over itself, but as I said, it's an orbit, okay? And this orbit is parameterized by the frequency of oscillation. Okay, first of all, you see that in solution space, the frequency of oscillation parameterizes somehow very nonlinearly the angle that is generated by this orbit, because here you have K0, 4K0, and so on. So it's exponential in parameter and linear in the solution space. Okay, so that's the first remark I would like to make here. The challenge was to have a lower model for this flow, which is transonic flows with shocks that develop on the suction side and on the pressure side of the earth. Okay, fine. Now this was the first brute force attempt to have a lower model for this flow. We had actually a lower model outside the colored region and a full model inside the rectangle here, and you see in white the full order solution and in color the low order model. You see that somehow it tries to fit to the shock, but it is completely I mean, the precision is completely lost in this region here, where the shock is really offset with respect to the low order model. So of course the problem is that once you have solutions that are advected either in time, like, so let's say solution structures that are either advected in time, as it is the case here, or in solution space or in parameter space, there is no hope with a linear combination to recover the position of this shock just by combining modes, okay? So our idea was, okay, let's exploit the nonlinear interpolation that Monge can provide us. Let's define a PDF from the square root of the Mach number and then map from a frequency that we know that we have in the database, K, for example, say 0.08, let's map each snapshot to the frequency that we also have in the database. It's K equal to 1.28, okay? And let's create those green artificial snapshots that we will include in the database in order to enrich, so to make what we call here data enrichment, okay, in order to improve the solution. And actually, just to give you an idea, this is the interpolation snapshot that we get in color and the actual full order solution that corresponds to that snapshot, and the agreement is quite amazing, right? It's difficult to understand to believe it, but it is true. And if you include those snapshots now in the reduced order solution, you see that now the low order model is able to fit almost exactly the full order solution, okay? Fine, but where's the catch? Why we are still talking about this if everything works fine? Well, it's because in order to have this artificial snapshot, we had to solve a problem, a nonlinear problem, which corresponded to a PDE, okay, taking into account boundaries, which was very difficult to solve numerically and expensive in time. Okay, now the challenge is to get to similar results with a fast and effective approach. Okay, so that's the challenge now. To do that, we resort to a Gaussian model of coherent structures. Okay, so the idea is, let's go back for a minute to this oscillation here. Our objective here is to follow this coherent structure, which is represented by the shock. Now, the plan is to split the problem into, on the one hand, is to find the mapping. Okay, on the one hand, we have the problem of finding the mapping, and on the other hand, we have the problem of finding a nonlinear interpolation for the solution. These are two separate problems. So we'll first attack the problem of getting the mapping right. And that's the way we go. So we first define a scalar testing function which will put Lagrangian markers at the place where we like. Okay, so the scalar testing function t, curly t, okay, will set the Lagrangian points, and I call them Lagrangian because we will move them around, that will be mapped by the mapping we are going to find, okay? And this criterion can be anything. For example, you can think of entropy above a certain threshold, okay? And I will give other examples in the following. Then, when I have these Lagrangian markers set on both the solution, let's say 0, and the solution, let's say 1, then we define a Gaussian probability density function which represents those points, okay? So we will actually take the points that we have defined by this testing function curly t and call them p plus high fidelity, which plus because they satisfy this criterion here, and then identify the Gaussian distribution which gives the best estimate of the IID realizations of the Lagrangian markers that we have set. And that's a very simple exercise in statistics. These are explicit formulas. So once we have the Lagrangian markers, we can get to the Gaussian distributions that represents the markers in solution. So let's say in snapshot 0 and snapshot 1. Okay, fine. Once we do that, then the Monge mapping, it's a matter of an explicit solution, meaning that the mapping that we found before by using a nonlinear PDE that was costly to solve, it just solved explicitly by classical, well-known formulas. So the mapping will be given by combination of the two average function, two averages by a convex combination of the expected values mu0 and mu1, and you have the covariance matrix, which is expressed the way you look here. Okay, fine. That's the story. Once we do that, basically, we go back to the parametric field that we wanted to interpolate. Okay, now we have the mapping, we have the parametric mapping, and we use that parametric mapping to interpolate non-linearly the two solutions. But as I said, the two problems are split now, okay? And the way we do that, it's just by what we call a convex displacement interpolation, because it's essentially an interpolation along the characteristic defined by the forward and backward mapping. Okay, so there are a few technical points here. The formulas might look a little bit complex, but basically the idea is the following. When you do linear interpolation between two snapshots, you are basically interpolating point to point, let's say, in interpolation space, okay? Now what we are doing is these 2 points, we are shifting them in space according to a mapping that we know how to find thanks to a Gaussian mixture model. Okay, we can come back to this. It's a little bit technical, but that's essentially linear interpolation along characteristics, which means essentially nonlinear interpolation, but with a very, let's say, simple background scheme, which is encoded in this formula here. Okay, so let me give a first example of what I'm talking about. We have the supersonic flow over a wedge. Okay, the supersonic flow over a wedge is parameterized by essentially the wedge angle. Okay, and the Mach number at infinity. In this test case, we are changing both the Mach number at infinity and the wedge angle. And we are remapping the solution in a reference plane. So what you see here, it's a reference plane corresponding to the average of the two wedges, okay? And the solution for Mach at infinity 5 is mapped here on the left, and Mach at infinity 8 is mapped on the same reference domain on the right. Okay, so left Mach equal 5, right Mach equal what I said 8. Okay, and wedge 28 on the left, wedge 22 degrees on the right. Everything is mapped on the same geometrical plane. Okay, reference plane, sorry. Now we set the markers here, the blue markers here on the left solution, and the red markers here on the right solution. Okay, now we have the Gaussian on the left, which corresponds, for example, to the blue markers on the left, which will be mapped to the Gaussian, not represented here, corresponding to the markers, to the red markers here. And what you have is the green, so the mapping results in the green markers, which are interpolated between the blue markers and the red markers. And the mapping that you have, so the vector field of the mapping is represented by here the arrows, which is very physical, very reasonable in terms of what you would expect. So let's see in terms of now solution what happens. So this is a cut at a given height, okay, of the solution. So you have the x coordinate here on the abscissa, and you have the Mach number on the ordinates, and you have the solution at Mach 8 in blue, the solution at Mach 5 in yellow, and then you have the interpolated solution and the exact solution. Okay, so one is a nonlinear interpolation, the other one is the exact solution for an intermediate Mach number and wedge angle, and they are almost the same. Okay, and that's systematic, meaning that the interpolation here is conducted for an interpolation parameter of 1/4, here on the left, and you have the interpolation parameter, which is equal to 3/4 on the right, and the fitting is almost perfect. Just to give you an idea, then I show for S equal 1/2, so meaning between, so here it's Mach 6.5, okay? You have the interpolated solution here on the left, and what would be the linear interpolation on the right, which is basically extremely not accurate, okay? Now, that's, let's say, half of the story, in the sense that now what happens if boundaries are there, okay? Now, in this case, taking into account boundary conditions was quite easy because we could, since it is interpolation along characteristics, we basically prolong so create a prolongement of the solution outside the borders of the domain by a constant, and the nice thing is that this constant is the exact solution, so there's no problem here. A different story is here for the transonic flow over an airfoil, where now we try to have a prolongation of the solution inside the airfoil and see how the characteristic interpolation will now behave for this kind of. So we have,
Désolé, je ne peux pas faire ça dans.
Okay, so this is Siri who of course, sorry about that. Now, so we have the solution, so it's a transonic flow. We have a shock wave, which is here on the left for Mach 0.77, a shock wave that is significantly displaced for Mach equal 0.83, and now we are trying to find the interpolation between the two with the technique that I explained you. Now, these are the markers, okay? And the markers are defined using a kind of Ducrot shock indicator, okay? Which basically is used in the framework of DG, of the actual DG solution. And we will be mapping the left cloud, the red cloud, onto the red cloud, okay? Now, once we do this, you'll have, okay, sorry, here it's Mach equal 0.8. It's the actual high fidelity interpolated solution here. And this is how it looks, the convex displacement interpolation. In other words, the interpolation along the characteristics, where we have a prolongation inside the airfoil, which is defined just by a Laplacian. Okay, so you see that around the stagnation point, the interpolation, it's basically senseless, okay? But let's see what happens far from the stagnation point, okay? And let's look at the two cats that are shown here. So one, it is in -0.1, okay? And the other one is in x2 equal -0.5, so a little bit farther away from the airfoil. So you see that compared to the linear interpolation, which is in black, okay? In the region of the shock, okay, the nonlinear interpolation, it's just very good, okay? Whereas far from the shock, in the, say, linear region here, the convex interpolation, meaning the interpolation along the characteristics, it's completely missing the point. That's basically due to the fact that the prolongation inside the boundary is not good enough to represent a reasonable solution for this problem. Okay, so what's the next step? The next step is to have a projection, an actual projection, in some sense, of the mapping that we have found, thanks to the Gaussian model, a projection in the space of the mappings which respect the boundary conditions. And that's basically what is explained here. So this projection that we call boundary-aware transportation of Gaussian models can be approached with several techniques. One technique, which is particularly efficient, is the technique that Tommaso has already developed for another problem, and he can maybe comment about that. It basically consists in having the mapping TG that we found by the Gaussian model projected with some regularization onto the space of mapping curly n, which is appropriately defined. Okay, so this is done both for the forward mapping and for the backward mapping here. And so we are able to project the mapping that we found by the Gaussian model, and which is not boundary aware, we are able to project it in the space of mappings that are boundary aware by this minimization technique. Okay, and we can discuss about this. Now, the convex displacement interpolation, or the interpolation along the characteristics, looks like the one before, exactly the same formula, except that now the mappings that we employ here are the mappings that are projected in the space of boundary-aware mappings. Okay, now let me show first the results for this case, and we go back to the problem that I showed before. And now you see interpolations for, say, 0.5, say 1. So we are moving from snapshot 0 to snapshot 1, let's say, and we stop at 0.25 or 0.75. So these are the kind of solution that we obtain, and already we see that, I mean, now the structure is preserved. There is nothing weird that is going on around the boundary. Now let's look at the error, okay? So the relative error that we have as the Mach number goes to 0.77 to 0.83 is the following. In blue, you have the linear interpolation. In red, you have the convex displacement interpolation. So the error is essentially divided by 5 to 4, okay? And on the left here, you have the error due to displacement interpolation in absolute value. You have the error in an absolute value due to linear interpolation between these two Mach numbers, okay? Now the question is, okay, and the plot that I showed you before changed completely of shape, in the sense that now the red curve and the blue curve are almost superposed. So again, the blue curve is the interpolation. The red curve, it's the exact solution. And it is just amazing to what extent they are fit. Okay, that's just non-linear interpolation. The black curve is the linear interpolation. Okay, now of course you will tell me what happens is there are several structures. So here we have a transonic flow which has two structures, okay, so two shocks, one on the pressure side and one on the suction side, okay? And what we will do, we will map the red dots onto the red dots thanks to the Gaussian model, the blue dots onto the blue dots, thanks again to the same Gaussian model for one Gaussian, and then project it into the space of admissible mappings, again through the same minimization technique, which includes a projection and a regularization term. Okay, so these are the kind of interpolated solutions that we get. We see already that they are very reasonable, okay? And the solution error that we get compared to the linear interpolation, it's less astonishing than before, and I will explain why in a second. And the why is the following. If we now see at the cats at different heights of the solution, okay, we see that on the So this was, let me just see how was it. So on the suction side, okay, which is here on the right, on the suction side, everything goes well, okay? So the interpolated solution almost exactly fits the full order solution, okay? Whereas on the pressure side, there is this shift between the two solutions. Okay, but as it can be shown, the mappings between the red dots here and blue dots there might have different time, let's say, parameter scalings, okay? This can be shown, and if we scale appropriately the parameter that we use to interpolate for the red dots and for the blue dots, we would get an almost perfect solution both on the suction side and on the pressure side, okay? But let me go through these and come to my conclusions. So the main point here is to have an explicable nonlinear interpolation model, that combines the computational, so our computational competencies and the data that it's available. Okay, so that's the main strategy that we are applying here. Now, we show example of learnings of both the approximation space on the one hand, and on the other hand, we show a path to have data augmentation or to have registration with an appropriate mapping. Okay, I will come to this in 1 second. And this represents an essentially non-intrusive approach, meaning that we can perform this interpolation, nonlinear interpolation, regardless of the model which is underlying the snapshots. So it's completely non-intrusive, regardless of the model or the scheme, okay? Of course, these are, let's say, conceptual results. There are huge possibilities of improvement and huge possibility of using it, in the sense that, as I was saying, we can use this approach to have a reference approximation space where the mapping by the solution space, and that's what I said, by learning the approximation space, or by learning, just improve the snapshot database by using, let's say, data augmented snapshots. That's the way we went, for example, in different other works. Or we can use it for registration, okay? Which is almost, when I say registration, it means to solve the problem in a reference domain. And I think that's all, and I'm happy to answer to any question.
Thank you, Angelo, for sharing your very interesting work. So are there any questions from the audience?
Can I ask a question?
Sure.
That was a very nice. That was a very nice talk, Angelo. It was really nice. And I mean, this is a nice mathematical concept, and you just extended this to the reducer of the modeling framework, and you've shown that it's working. I thought that was very nice. Now, the question I have is, so are there other techniques? How would this approach compare with alternative approaches that could, what other people are using? To me, it sounds very much like nonlinear manifold type of interpolation. And so how would this fit in that in the grand scheme of things?
Okay, so indeed, there are ideas that go in this direction, to my knowledge, that are linked mostly to artificial neural networks to get to the same results. Okay.
Right.
So how does it compare? So it compares, so my answer can be a little bit political in the sense of saying, look, artificial neural networks, you don't know exactly what you are doing. So it's this first sentence here, it's this approach is an explicable nonlinear interpolation. So you know what you are doing, okay? The result can be good, exceptional, bad, but you know what you are doing. You know the elements you are introducing in your model. In ANN, it's not exactly known what you are doing. So there is not this notion that Isam was referring to a while ago of convergence, of convergence, and moreover, you don't know exactly what you are doing. So this is kind of political answer. On the other hand, there is a practical answer. The fact is that here we have two snapshots, okay? So we have two snapshots and we are able to do a nonlinear interpolation exactly because we inject a model, okay? If you were to do ANN, you need tons of data, okay? So in this sense, this kind of approaches can be used together with machine learning techniques, but they significantly improve the information content because you are putting model in it. So this is one answer. And then there is another technical aspect is the fact that these mappings are boundary aware, and that's not an easy task in general. So there are other authors that are attacking the same problem in very smart ways. I think that the real challenge is how to deal with boundaries. I don't know if I answered your question, but I tried to go along the path of your question, at least.
That was very good. Thank you. Thank you.
Thanks, Trian.
Okay, any other questions or comment? Well, if not, I'd like. Okay,
sorry, Angela. What really quick, and this is a little bit crazy. This is a little bit crazy, but I've just I've meant to ask this for a long
time. The discussion.
So, how did you come up with this idea? I mean, it seems to me that it's not like Angelo, so it's not like something that is very, you know, what was the thought process? It's very nice, but how did you approach, you know?
Thanks a lot for this question, Trian. So the question is the following: is that quite some time ago in the PhD of Damiano Lombardi, we were looking at optimal transportation for registration at that point. But then we said, look, this optimal transportation thing, I mean, it's just amazing. And because you can get this mapping, okay? And starting from there, we played also with Haitham and Michel, and we have been suffering because this optimal mapping, it's a mess to get. But there are mappings that are known explicitly. So with Gaussians, the mapping is known explicitly. So this looks like a good compromise between our things.
Very nice, thank you.
Thanks. And Trian, we have to organize a session if you are available, and I take the occasion in Virginia Tech. So
sure. Yes. Yes. Sure. Absolutely.
Thanks.
Angelo, we have an additional question from Francesco Romol. I hope it is. He asked, does the consistency of the method relies on the fact that the considered PDEs can be seen as gradient flows? If it is true, have you tried interpolation in Wasserstein spaces for problems not interpretable as gradient flows?
Okay, that's okay.
Stuff.
It's a very good question, and I only have a partial answer. Okay, we can show, as this gentleman is suggesting, that, for example, many classical problems, like, for example, heat equation, but even some classes, okay, all the Riemann problems, so heat equation, Riemann problems, nonlinear heat equation, simple wave problems, they can exactly be solved by optimal transportation. Okay, so this is exact. So underlying compressible Euler equations, there is this structure. Okay, there is this structure. Now the question is, what happens with equations that do not have this structure? Well, if you don't have this structure, I agree with you that it's senseless to use this structure. If you don't have this notion of advection of displacement, it's not really interesting. But I mean, that's a superficial answer, but it is a little bit my feeling. I hope I answered somehow, even superficially, to this question.
He thanks you.
Yeah, so by the way, I'm not able to get back to something that I can manage here, so sorry about that. I don't know how to stop sharing, but whatever.
Okay, no issue, Angelo.
Okay.
So if there are no other comments or questions on Angelo's presentation, I'd like to thank again all the speakers today for sharing their work and their experience on these topics, and also the audience for attending and asking a lot of questions, especially Traian. Thank you for sparkling the discussion. And well, I'll leave the final remarks to Angelo.
Okay, thanks, Angela. The final remarks will be very short. We can further discuss these issues in the sense that, okay, what we showed here, I mean, at least the last presentation, is not yet applied to the Volkswagen test case, but in the end, that's the objective. We started with simple, let's say, 2D cases with problems that we fully manage, and then our plan now is with the help of Optimad and of Volkswagen to move to the more challenging, in a sense, test case of Volkswagen. This is the second occurrence of a ARIA seminar. We will certainly organize another set of seminars on a specific topic to be decided. Please stay tuned. And please, if you have additional comments about what was presented and how it can be cooked together, it's free speech, and I invite you to just come to the podium and express yourself. Okay. So if there are no more comments,
can I say?
No, that's Traian.
Since Angela encouraged me, so I'm gonna go. But I have a very quick comment and question actually. So to me, this was a highlight of the ARIA project. I think that's one of the main strengths. The fact that you look at industrial application like Volkswagen, like what Karsten, Marcus, and Haissam were talking about, and then how reduced order modeling can help. But I'm in an academic, so this was great. But you see, so my question, and I think there are other people who want to ask the same question, is how do we get to use, I'm a modeler, how do we get to use, try, test our models in something that let's say Volkswagen is interested in? So the Ahmed body, what are the requirements? It's a good problem. And what are the requirements for, what's the simplest test case that, you know, one can try to test his or her model on? That connection between academia and industry, I think that's what I would like to ask. Is there such a, what's the easiest way to collaborate, I guess?
down a document with all the specifications of the armored body, and we're happy to provide any data you need, or also to change the test case if that's necessary, right? So that's what we can offer, right? And if it's already too complicated, then we can also think about going one step back into NACA profiles or backward-facing steps to have some separation at least, right? So just well, I can first of all share this document that we created that describes the test case, and if you think that's not the right thing you can tackle with the methods as they are at the moment, then just let's start the discussion, and we can apply any change you would like to see, and come up with let's say a simpler version, which is also representative of the original problem that we'd like to tackle.
Exactly. Okay, sounds good, Karsten. Thank you.
So Traian, since we have, if you are available and to be organized, but that can be a kind of theme for organizing a session in Virginia Tech whenever it is okay for you, and give it a little bit of breadth if you like.
Absolutely. I would be happy to. I mean, I can, so you mentioned this, so I would be happy to and talk with you and decide how to go about it. But I would say that coming up with a set of, like Karsten was mentioning, like a set of test problems. This is something that in the ROM community, academic ROM community, this has been mentioned. It would be great to have a suite of test problems that the industry is interested in, and then test the many multitude of plethora of ROMs and see, where we stand. I think that would be really great. And there should be a discussion, from both sides, like what do we need? And I think that would be great. That's a great idea, Angelo.
Yeah, it's basically your proposition.
This has been around for a while. I mean, I think people, individuals are talking about this, but it would be nice to have a group together. So let's talk about this. Absolutely, yeah, sure.
Sounds great. Okay, thanks a lot, Traian. Any other comment? Tommaso, you are too quiet today. What's wrong? He's not there. That's why he was too quiet.
No, I'm here. No. I mean, I hope.
Okay. So no specific comment.
No, I think with Traian about the fact of test cases, I think it's very important.
Very good. So thanks everybody. So stay tuned, and please don't hesitate to exchange information and to contact us if for further details. Okay. Thanks a lot. Bye.
Thank you, everyone. Thank you. Bye-bye.
Thanks.
Bye-bye.